student. Let us begin lectures on machine design part 1. This is lecture number 15 and the topic is design of keys and splines. Now in last two lectures we have known how to design common types of fasteners, namely the knuckle joints or the cotter joints. Now in those joints mainly the purpose was to transmit tensile or compressive force from one member to the other, but there are cases and many cases in a machine where we have to transmit torque from one shaft to another shaft which are which have the center line the same. So these are very common things and we have to design a fasteners such that the torque can be transmitted from one member to the other quite efficiently. So we are now going to start discussions on keys and splines. So these are the again one kinds of fasteners, that is the non-permanent type of joints where the torque can be transmitted from one shaft to the other shaft. So these are very important things and the design is quite difficult, exact design, exact analysis is quite difficult, but we are going to design give some guidelines of the design. Now let us first come to the basic types of keys. So we are going to divide the lectures into two parts. One is the design of keys and another is design of splines. In some books you will find splines are taken to be one kind of keys, but for our discussions we are keeping them separate. So let us see what are the different types of keys. Now the purpose of the keys, as I said, is to transmit torque from one shaft to the other shaft. That is, if we have a shaft over here, then this is one shaft. Let us think of another shaft which is concentric. So these are two shafts where the torque has to be transmitted from this shaft, from the inner shaft to the outer shaft. The means of doing so is by using the keys. Now the keys are a small piece of some material which is the same as that of the shaft material, where these are normally rectangular in cross sections. So here we see that what we do, we cut two slots in both the shafts and then insert one small piece which is known as the keys. So here we have cut one keyway and this is key. If you draw it in further details, then what you see is that, let us draw the outer shaft. The outer shaft, here we can get, so this is that part of the outer shaft. Where this key slot is cut. The inner shaft, again we have another, this is the inner shaft where another slot is cut. Normally these two heights are equal. If the total height is h, then this is h by 2, and so this is the slot for key and we insert a key over here. Now there is a small clearance, a tolerance. This is because of the machine fitting. So this is a tolerance, a very small tolerance that also depends on the keys, the dimensions of the keys, but there is some tolerance, and so this is how the key looks like in a key slot. Now this part, which is the corner of the keys, this part, this is now little chamfered. That is, if you look again in a little more deep in a little more details, then the keys will look like the cross section, so this part which is little chamfered, so this angle is almost 45°. So this is how it looks like near the corner. So this is roughly the design of the cross sectional design of the keys. Now the key which I have drawn is one kind of key. There are various kinds of keys which use the same principle, that is there is a slot cut within the shaft and some extra material is inserted such that the a firm binding is formed. Now this kind of key which I have drawn is known as the sunk key. Now there are various kinds of sunk keys. One is the rectangular sunk keys, so this one, and rectangular sunk keys, if it is drawn, it will look like the following. So here, so this is rectangular in cross section, so this is the key, but normally there is a taper here. So this taper angle, let us call it beta. Now taper angle is such that this is 1:100. This normal taper angle is that, so that means tangent of beta is equal to 1/100. So this is the normal taper angle, and this cross section is rectangle. This is normally known as the width, denoted by W. This is height H, and this is the length of the keys. Now this is the rectangular sunk keys. If the W equal to H, then of course the cross section is square cross section and we call it square sunk keys. Then parallel sunk keys, of course this beta equal to 0. So in that case, for the parallel sunk keys, for this case beta is equal to 0, that is there is no taper angle. Now gib head keys, this term gib you have already come across while joining designing the quarter joint, at least the type of quarter joint which I said. There is one joint called gib head quarter joint. Now gib is again, gib head keys, it looks somewhat like here, like the following. This is so this is the front view of the gib head keys. What is the purpose of this? This is known as the gib. This part is known as the gib, and what is the purpose? That is to arrest the this is normally used in order to withdraw or in order to draw out the keys or fix it back. So if you look at the assembly, then it looks like here. So this is the shaft. Now again this is the shaft, and this is another shaft. It is difficult to call it shaft, but let us call it disc in that sense. So we have to transmit torque from this one to that member. Now what we do, we cut this slot over here. So we introduce this gib head key. So this is the gib head key. So this purpose is to, this is the key slot. So this purpose is to draw it easily. So this is known as gib head key. Of course there will be a taper angle, again the taper angle will be 1:100. Then the feather key. Feather key is another kind of key where the key is an integral part of one of the shaft, either outer shaft or inner shaft, and the purpose of feather keys is to accommodate axial motions. That is, if you draw one shaft, there may be a key which is integral part of it. So, this is now integral part of the. Now, it may be machined this way, or it may be set by set screw. It may be screwed here, and we put another disc which key slot cut into it and then insert. So, you see that if you move it this way, that way, the key provides enough flexibility in moving in axial directions. So, this is the feather keys. Then another kind is the Woodruff keys. Now, let me draw the Woodruff key. Woodruff key, again, if this is the shaft, Woodruff key is somewhat like this. It is a semicircular key. Now, in 3 dimension it looks like this. So, it has some advantage. One advantage is that this key can be fixed in various orientations. So, it can accommodate some misalignment of the of this assembly. So, this misalignment can be taken care of, but it has one drawback. The drawback is that there is a deep hole cut into this shaft. So, if you look into the shaft cross section, it becomes, so if this is the shaft cross section, then we have to cut a deep hole into it. So, when a deep hole is cut, so this is a slot cut, so therefore, it reduces the strength of the shaft. So, now the strength of the shaft gets considerably reduced. So, this is one of the disadvantages of the Woodruff keys. Now, these are roughly the types of sunk keys. Now, there are other types of keys which I am going to explain. One is the saddle key. The saddle key, now here suppose this is one shaft, part of the shaft, inner shaft, and let me draw the outer shaft. This is the outer shaft. And here we draw, there is a key cut over here, similarly over here. Now, here the slot is cut within the outer cylinder. So, therefore, this contact is maintained. Now, this is again square cross section. So, therefore, the contact is maintained because due to the friction force. Therefore, it is expected that it will not be able to take a large torque. So, the strength of this key is considerably less, and it is used for the light load applications. Now, this is one kind of saddle. There is another kind of saddle which is a round saddle, that is, here instead of this the flat face, we have a curved face and the radius of curvature matching exactly. So, now we have another kind of saddle. So, this is one kind of saddle, another kind of saddle is that another kind of saddle, here the slot is cut such that, I mean this key is made such that it actually matches the profile. So, naturally the torque transmitted is again due to the friction force and therefore, it is considerably less. So, these are the saddle keys. Now, let us come to another type which is known as the tangent keys. Let me draw the tangent keys. Let us draw the inner shaft and the outer shaft. So, this is the outer shaft and this one is the inner shaft. Here we draw the tangent key. The tangent key looks like tangent over here, but it is grouped this way. So, there are two keys. This is one tangent key. Definitely it can provide torque in one direction. You will see that if one direction, if the torque is given in some direction, in one direction, then there is a chance of slippage, whereas if the torque is applied in the opposite direction, then the chance of slippage is quite less. This is avoided by making two offset tangent keys. So, the tangent keys, again there are two such tangent keys. With some offset angle, let us say 60° angle. Okay. So, now it can transmit torque in both the directions. So, these are the tangent keys. Sometimes we use the round keys. Now, how do they look like? Let me draw the round keys. They, as the name suggests, they are round in shape. So, let us say that we want to fix one shaft to another shaft. Then what we do, we drill a hole over here and then place a key. So, if you look from the side, then it looks like this is the inner shaft, this is outer disc and the key is here. So, this is round keys. Now, what is the advantage of round key? Here the round key, the main advantage is that this is drilled after the final assembly. So, we can take the this advantage that the alignment can be done properly. Also, it can withstand quite high amount of load. So, the capacity is quite large as well as the alignment could be fairly acceptable. Now, these are the different types of keys. Now, we have to go to the design of this key, that we will do as a next task. So, let us now come to the design of keys. We are going to demonstrate the design taking on first the parallel, only the sung type keys. We take first the parallel keys and then the taper keys. So, let us first concentrate on the parallel keys. So, here this is the inner shaft, and we have the outer shaft over here. So, this is the part of the outer shaft, and we have a parallel key over there. Now, so this is the key, and this height is the geometry of the key. This height is h by 2 and this is w. Now, w is sometimes taken to be almost equal to d by 4, where d is the diameter of the inner shaft. So, this is the rough estimate of the w. Then what are the forces? Suppose we want to apply, we want to transmit torque here. So, therefore, when we apply a torque, then a force is experienced. So, there will be a force over here and another force on the key. So, if you draw it, then on this part there is a force and on this part there is a force, the magnitude of force being F and F. So, what is the value of F? That again depends on your M. So, therefore, F will be equal to M divided by d by 2. Then we have to check for the design. Now, let me look at the key, solely on the key, and try to find out the design. So, this is key and it is subjected to force F, force F. This distance of course is W and this is H, total H, H by 2. So, therefore, you see, if you look at the total sections, then it becomes so this from this half it is subjected to pressure such that the net force is F. Now, then there are two kinds of stresses developed. One is the crushing stress. So, the crushing stress will be equal to sigma compressive stress will be equal to F divided by the total surface over which the bearing pressure or the contact pressure occurs, that is H by 2 times L, where L is the length of the keys. There will be the shear stress, and shear stress will take place along this surface. So, the total shear force is again F and the shear stress is equal to total force divided by area, which is equal to W times the L. So, these are the expressions. Now, in order to have a design, good design, then sigma c must be less than the allowable compressive stress, that is the bearing crushing stress, and tau must be less than tau allowable. Now, once we have designed a key, then we go for checking this. But one way of designing this key is now to compare the two strengths. Now, we have to define the strength. Now, strength of the key is the maximum torque that can be transmitted from one shaft to the other shaft. Definitely, it depends on sigma c allowable. So, if we consider the strength due to crushing, so crushing strength of the key, that means the maximum torque that can be applied while sigma c becomes equal to sigma allowable, that is the allowable crushing stress. So, now in that case the design procedure will be sigma c is therefore F is equal to h by 2 L times sigma c, which is equal to sigma c allowable, and M, this is let me call it crushing strength, that is the maximum torque that can be transmitted, that is equal to F times d by 2. And what about, so this is one form. Now the shear strength, that is the maximum torque that can be transmitted while tau reaches the value tau allowable, is equal to is can be taken to be the following, that is F is equal to omega WL times tau allowable, and therefore M shear is equal to WL tau allowable times d by 2. Now a normal way of designing is to equate this strength, that is we want that the strength in shear should be equal to the strength in against crushing. So now MS equal to MC, that gives H by L, H by 2 times L times sigma c allowable times d by 2 equal to WL d by 2 tau allowable. Now if we take the rough estimate, that is W is almost equal to d by 4, then what we get is the following, that is here the d by 2 cancels, and ultimately when we use that, then we get the following results. Even L and L here cancels, and we get the usual expressions between W and H. Once we write that, then it becomes W is equal to H by 2 sigma Ca divided by tau allowable. Now normally sigma Ca divided by tau allowable is almost equal to 2. So it cannot be less than 2. So therefore W is taken to be equal to H. So this is again, this key is the square key. So in the square key, of course, we have approximately the strengths are equal against crushing and shear. Now how to design the length? Now this length can be designed from the strength considerations of the shaft as well as the key. Then the strength of the shaft is taken to be the following, that is the maximum torque that can be transmitted the maximum torque can be transmitted, this is equal to tau if you consider this shaft, then the maximum torque can be transmitted is tau is m divided by pi by 16 d cube. For the maximum value, this is tau allowable. Now let me call by prime when we talk of the shaft. Now the strength of the shaft is pi by 16 times d cube times tau allowable prime. Then we can decide L, the value of this length, that is equating m and ms. So what we do, that we equate m equal to ms, and when we do that we get the following expressions, that is pi by 16 d cube tau allowable prime is equal to the shear W L d by 2 tau allowable. If tau allowable prime and tau allowable, they are taken to be same. Now we assume that tau allowable prime is tau allowable because they are made of roughly of the same material, and we consider W is roughly equal to d by 4. This is the usual way of designing. Then L will be equal to 1.5. L will be equal to so the relationship will be L will be equal to 1.57 times D. If you do this calculation, so ultimately what you get is the following. That is, from this expressions we get L equal to about pi by 2 d, which is almost equal to 1.57 d. So this is the minimum length required, and if you have this length, then the strength of the shaft will be equal to the strength of the keys as far as shear is concerned. So in this analysis we have equated all the strength, that is the maximum capacity of this shaft to transmit load from maximum capacity of the shaft and the keys for transmitting load from one member to the other. So this is one way of designing the keys. But if you go for the taper keys, then the analysis becomes quite complicated. What we see here, let us check the design for the taper keys. Now what we have there is, this is the taper key, and if you have this cross section, then it is the cross section. So therefore, once it is fixed, then we have few forces. One is this normal force F1, another is normal F2, and then the friction force. Now here for the taper keys, normally the mode of transfer is through frictions. So what we can draw is, this is the shaft where this is the outer shaft is drawn over here. So this is the inner shaft, this is the outer shaft, and there is the key. Normally there is a clearance. So therefore the torque is transmitted over here. So now if you look at the key, then there will be the friction between these two surfaces, and this friction force will act. So therefore the friction force will act on the outer shaft, and here it will act on the inner shaft in the opposite directions. If you draw the free body diagram of the key, then there will be friction force here and friction force in that directions. So that depends on the normal pressures. So this is mu times F and mu times F. So normal pressures will exist. Hence the maximum torque that can be transmitted will be equal to, the torque will be equal to mu times F times the diameter by 2, that is the radius. So this is the maximum torque that can be transmitted from the taper keys. But this analysis is not completely is very conservative, that is, if you design with this approach, then you will have to design very conservatively. Otherwise, there are lots of other things which I am going to discuss briefly. But coming to our original analysis over here, what we see is that there are two forces. If you draw the free body diagram looking from the side, then you can see there are two forces, F1 and F2, and F2 will be equal to F2 is normally the pressure times B or W times L. So, this is the total surface, this is W and this is H. So, therefore, the total force F2 is P times W times L, and this F1. Now, how does F1 develop? Now, we will have to insert this key, therefore, we need to apply some force from here. Let us say we apply F0 here, then there will be the stress developed, and there will be the friction force. Now, it acts like an wedge. So, there will be friction force, this friction force will be mu times F1, and this will be again mu times F2 on this side. So, if you draw the cross sections, then again we have one component of F1, but there will be one friction force acting over here. So, there may be one friction force here which is equal to mu times F1, and there may be the opposite friction force mu times F1. So, these are the free body diagram. These are all the forces on the keys. Once we make the analysis, that is, write down all the equations, then what we get is that so F2 is P, the maximum pressure can be taken, that is the pressure within this pressure on the shaft, this PB times L. Then this angle is beta. So, if you write down all the expressions, ultimately what you get is F0 is equal to twice mu F2 plus this is F2 tangent beta, where we have neglected some terms like mu times cosine beta or mu times sine beta, etc. These are neglected. So, with this analysis we find out the required force F0. Now, if we apply some F0, then of course F2 will be developed, and that will give the required pressure, because ultimately the torque depends on F2. But the taper keys, the design of taper keys is very complicated because of the following reason. Let me explain briefly what are those reasons. You see, there will be always some clearance between this shaft, between these two shafts, inner shaft and let us say this is the outer shaft. Let me so this is the outer shaft and that is the inner shaft. So, this is outer one, and this one is the inner one. Okay. So, there is a clearance over here where the key is fixed. This is the taper key is fixed over here. Now, the friction force acts maybe in this directions and that directions. There may be the normal force N and N. They make since the distribution is not a priori known. So, therefore, it is difficult to say whether in these two the line of action will be same. So, there is a little offset, but what is important is that there is a contact between two shafts in this region. So, this is the contact region, right, and the contact pressure develops. So, there is a contact pressure. The exact distribution is difficult to say, but now roughly it is expected that this kind of cosine distribution is exist. Now, when it rotates, when you apply a torque over here, so the friction force develops. So, friction force develops. So, now we have two kinds. So, the total torque which can be transmitted is not only due to the key, due to the friction between the keys and the shafts, but also between the two shafts because of this contact pressure developed. So, the total torque will be maybe the MT, the total torque is equal to the torque due to this friction force F, if I call F, this is distributed force, plus torque due to mu F, that is this part which I call F, let us say F and F. So, torque due to F and the torque due to N, because two N's here, if you draw this the key, then in one side the distribution looks somewhat, one side this is parallel and another side is has taper. So, if you have a taper, then roughly the distribution is somewhat triangular, and in that case the normal force here at the center, but here the normal force may be somewhere offset here. If the total normal force they are to be balanced, so this is the normal force, but there is one offset between the line of action of these two forces. So, there will be a torque, a moment developed due to the distribution of the normal force. All of them taken together will yield the MT. That is, MT is really not only due to the key, but also due to the friction force between two shafts. But while design, we make the design very conservative and do not consider this torque, but in real analysis it should come that way. Now, now we have considered the design of the the parallel keys this way, that is, we have taken the distribution of force. If you take the this is the distribution, if you take this distributions, then we have considered the force distributions to be uniform throughout. But it may so happen that the distribution sometimes are taken not uniform, but some triangular distribution, something like this. Here on the other side, of course, similar distribution will take place. But what is important is that in that case, of course, the analysis changes, the whole analysis changes, and we will have to again see this is the maximum pressure P max, and the maximum bearing stress will be equal to P max divided by, if this is per unit length, so P max divided by H by 2 will be the maximum bearing stress, that is sigma B will be equal to P max divided by H by 2, whereas tau max here will be equal to sigma divided by P max divided by this length, that is equal to W. And we have to again calculate the strength, again once due to the shear force, shear stress, and another due to the crushing strength. So, the analysis really becomes complicated. They are given in some design handbooks. The analysis of the keys is very complicated, because no even very exact, not any exact analysis is done so far, only some experiments are carried out with the help of photoelastic apparatuses, that is the photoelastic experiments are carried out, and we have found out roughly the empirical relationship. These are tabulated in various, so the design guidelines are given in various handbooks. We have to consult different handbooks while designing such keys. So, this is all about the design of keys. Now, let me go to the splines. Then splines are again a number of keys which are integral parts of the shaft. So, what is done is that, let us consider the shaft here. So, in one shaft a number of keys are machined. So, they are keyed by, these are machined. So, there are number of keys here. So, if you look from the side, maybe it looks like, and these are all integral part of the same shaft. The other shaft, which is the outer shaft, will have again key slots cut, and they are along the axial directions. So, therefore, what is expected, that if we mount one shaft to the other, then it can slide along the axial directions. The profile of the cross sections, they vary. There may be straight edges like the rectangular, as you see. So, this kind of edges will be formed. Also, there may be triangular pattern, something like this, or involute edges. Now, what are involute edges? The gear profiles, for example, are involute gear profiles are possible. So, involute edges are there. So, involute edges these are the involute edges. Well, this is for the external spline. There are few circles involved. One is known as this base circle. This is the base circle. Then this another is the pitch circle. These circles are useful for generating this involute profile. So, pitch circle and this distances, this and those distances, this is called dedendum and this is addendum. So, there are terms called dedendum and addendum. This distance is the tooth thickness, and if you draw a tangent to this base circle, then we get an angle. This is the pressure angle, which is very important for force transmissions, and this angle should be chosen such that the maximum torque can be transmitted. Now, what are the advantages of involute edges, involute profiles? One is that the sharp corners are avoided. Here, if we use that, then sometimes these are chamfered. So, the sharp corners are now removed. So, here there is no abrupt change in geometry, therefore, the stress concentrations may be quite low. But another advantage is that the involute edges can be generated in very standard way. So, there are different standards. Now, these are different kinds of splines. Now, different standards for keys, we have to maintain some standards. So, there are different standards used for the keys. For parallel keys and keyways, we have IS 2048. There all the informations about the width, length and the height are given, also tolerance, etc., etc. So, when we have to use such keys, then we will have to look up into those standards. Tangential keys 2291 formed in 1963, taper keys also you will find in some books 1974. Anyway, the standards were reaffirmed in 1980. So, this is the latest. But taper keys and keyways you will find in 2292, give head keys and keyways in 2293, Woodruff keys and keyways in 2294. So, these are different standards for keys. Different standards for splines. Again, for straight slide splines, this is IS 2327. For external involute is this one, where this is this shaft, and for internal involute, this is again the same. So, internal involute and this is external and this is internal. External involute 3665 and internal involute 3665 again. So, these are different standards. Now, let us come to the last part, that is effect of keyways. Now, the shaft strength factor, which is that because of the keyways, the shaft strength of transmission of the torque gets reduced, and it gets E equal to 1 minus 0.2 times W by D, minus W is the width of the keys, and minus 1.1 times H by D is the height of the keys. Now, the strength factor is the strength, that is the maximum torque bearing capacity T max without key, that is this is with key, without key, and this when divided by T max with key, this gives the value E. So, therefore, the strength gets reduced by some factor. Similarly, the angular twist factor, that is the angle by which a twisting takes place. You remember the well known formula for the twisting of a shaft. The twist, angle twist, it increases by some factor. Again, this is empirical relationship, and this is equal to 1 plus 0.4 times W by D plus 0.7 times H by D. Again, it depends on W and H. That is the angle by which the shaft will rotate, theta, it increases. So, theta max, that is the maximum angle, theta max with key divided by theta max without key, this is given by this factor k theta. So these are the things which are to be considered while designing a key. Now we come to the conclusions of this lecture. We have learned how to design a keyway and a key. There are various kinds of keys. There is another thing which is very similar to key, but it's not a key, and it is much more longer and has much more strength. This is known as splines. They are very, very effective and very much used for transmitting torque from one shaft to the other shaft. But there are various advantages associated. That is, the strength of the shaft decreases because of the keys, as well as the twist factor, the angle, the deflection gets increased. So these are the pros and cons of keys, but they are very, very useful machine elements and are to be designed with proper care. So this is the end of this lecture. Thank you very much. We are discussing different kinds of fasteners, and fasteners are non-permanent type joints where the members could be disassembled according to our will and without damaging the component parts. So threaded fasteners are one of the very important kinds of fasteners, where of course as the name suggests, there are threaded members. In today's machines, most of the machines will have different kinds of threaded fasteners. Normally, a rough estimate is that about 60% of the machine elements are now threaded, have threads. So and the fasteners types are threaded fasteners. So we are going to discuss different kinds of threaded fasteners in today's lecture. First of all, let us see what are the different types of threaded fasteners. Now the first name which comes is the bolts with nuts. Now this is a very common type of threaded fasteners which all of us are acquainted with. Let me draw a rough diagram of the this kind of threaded fastener.